Hi guys, this is a video on chapter 8. We're going to cover sections 8.1 to 8.3. We've looked at them in the Zoom session, but I wanted to give you a complete overview of these sections along with some solved examples. Now, I'm doing this video a little bit differently from the ones before. I'm not going to be writing as I go along just to save time and try and make this video quick. What I have done is I've pre-written the notes, and you can follow along in the notes, and whenever appropriate or maybe even all the time, to indicate where I am, I'm gonna have a red mark on the left of the screen like that. Okay, so I hope this makes sense, even though I'm not writing as I'm going. And I will, of course, email you guys these notes as well. Okay, so the first thing we're going to look at is Markov's inequality. What does that say? If x is a non-negative random variable, then for any positive number, the probability that x is bigger than or equal to a is less than or equal to expectation of x over a. Now, what is the proof of this? That's very simple. I will quickly write it down over here. So the proof of this, you have that the expectation of x is the integral from from 0 to infinity, because it's a non-negative random variable, x times f of x dx. Okay, so let's write down that integral in two separate ways: 0 to a x times f of x dx plus integral a to infinity x times f of x dx. Okay, now let's take a look at this second integral over here. In the second integral, all the values of x are bigger than or equal to a, right? So you can say this expectation is bigger than or equal to, and of course this first integral is bigger than or equal to 0 because x ranges from 0 to a, and f of x is a non-negative non-negative function. So this first part is bigger than or equal to 0. The second part, you can replace the x by a, and you would only get smaller, right? So if you replace the x by a, all the x's are bigger than a in there. So replacing it by a, you'd only get smaller, and I'll put a to infinity a f of x dx. Okay, well, what is that? Pulling the a out, you have a times integral a to infinity f of x dx. But what is this integral? Is a to infinity f of x dx. That's exactly the probability of x being bigger than or equal to a. So you have a times the probability of x being bigger than or equal to a is less than or equal to x, which is just this exact Markov's inequality rewritten in a certain way. Okay, so that was just a quick proof of that inequality over here. Okay, now Chebyshev's inequality is Markov's inequality applied to a certain random variable. Okay, and once you apply it, you get a certain interesting result. So what do you have in Chebyshev's inequality? You have that probability of x minus mu bigger than or equal to k. So the probability that x is at least k away from its mean, mu is its mean, is less than or equal to its variance over k squared. All right, so look at the first sentence over here, and let's start at the very top. We have Chebyshev's inequality. Now, since x minus mu whole square is a non-negative random variable, we can apply Markov's inequality. And for any positive k, apply, so instead of x up here, you'll have an x minus mu squared, all right? And that is bigger than or equal to k squared. So this is what I'm saying. That's the first line over there, okay? And, you know, that's just equal to the probability of the absolute value of x minus mu is bigger than or equal to k. Okay, so if you want, you can intuitively think of it as you're applying it to the non-negative random variable x minus mu squared. You seeing that is bigger than or equal to k squared, That's the same as looking at probability of x minus mu and absolute value bigger than or equal to k. Well, by Markov's inequality, that is less than or equal to the expectation of this random variable over here divided by this number over here. That's the A in Markov's inequality, and this was your random variable x over here. So that's what you have, and that, you know, the top expectation of x minus mu whole squared is the variance sigma squared. Denominator is k squared. Okay? So that's what you have, and you can get a bound. Now, you don't have to obviously look at x minus mu whole squared. Really, the goal was to look at this x minus mu in absolute value bigger than or equal to k. So you have that is less than or equal to the variance over k squared. So this is really Chebyshev's inequality right here. And you can estimate how, with what probability the random variables k away from the mean. Okay, so let's take a look at an example over here now. Suppose the number of people buying frozen yogurt at a racetrack in a day is a random variable with mean 200. Find a bound on the probability that the number exceeds 400 on a particular day. If the variance of the daily sales is 75, then what can you say about the probability that the sales between 185 and 215? Okay, so take a look. So in the first case, what do you have? You know the mean of the random variable, and you're asked find a bound on the probability that the number exceeds 400. Well, in part A, you don't know anything about the variance, so Chebyshev's out of the question. Let's look at Markov, just scrolling up. You have probability x bigger than or equal to a. So over here, our a is 400. So we start off by let x be the number of people who buy frozen yogurt at racetrack in a day. And the probability x is bigger than or equal to 400 is less than or equal to the mean, which is 200, over the a value, which is 400. So this probability is less than or equal to 1/2. Okay, you see right here? Okay, now let's look at the next part. If the variance of the daily sales is 75, so you know the mean is 200 and the variance is 75, then what can you say about the probability that the sales is between 185 and 215? So here you go. You have probability of x being between 185 and 215. Well, what do you know? That's exactly a symmetric interval about 200. So this is 15 around 200 on both sides. So with the probability of x minus 200 less than 15, that's what we want. And Chebyshev doesn't tell us that. Chebyshev just tells us the probability of being away from the mean. So, well, we want what's the probability of being within the mean. So let's look at the complement, and Chebyshev can comment on the complement. The probability of x minus mu bigger than or equal to 15, according to Chebyshev, is sigma squared, which is the variance 75 squared. Oh, the variance is 75, sorry. Divided by this a value squared. Okay, so it's 75 over 15 squared, 75 over 225, and this probability is less than or equal to 1/3. Well, since this probability is less than or equal to 1/3, you know that that would mean that this probability over here has to be bigger than or equal to 1 minus 1/3, which is 2/3. Okay, so does that make sense? So you see, just knowing a little tiny bit about a random variable helps you get estimates on what's going on with the probabilities of, maybe one-sided estimates of what's going on with the probability of being bigger than a certain number, or probability of being within a certain value of the mean if you have the variance. Okay? All right, so let's move on to another example. Now, let's see. If the variance of a random variable is 0, then that means you know the variance, okay? Then let's see what happens. The probability of x minus mu, we're looking over here in this line, probability of x minus mu bigger than 1 over n is equal to the variance over 1 over n squared, right? So, but 0 over anything, that's 0. So you know the probability of x minus mu being bigger than 1 over n is 0 for all n. Okay, that's nice. Then you take a limit as n goes to infinity, and you have, that means 0 equals the limit as n goes to infinity of the probability of x minus mu being bigger than 1 over n. We're in this line. That is, you can take the limit inside the probability of limit n goes to infinity of x minus mu being bigger than 1 over n. Well, what is that? That's the same as you can say if you wanted. Let me write that in here. That is, if you like, is the probability of x minus mu being bigger than 0, which is the same as the probability of x not equaling mu. And you know that has to be 0 all the way here on the left. Okay, so the probability that x is not equal to mu is 0. That means the probability x equals mu is 1. Okay, so what does this tell you? This result tells you that if a random variable has variance 0, then it's always equal to the mean. Okay, and you probably heard that phrase somewhere. If something has high variance, then, I mean, I've said it to you guys in class that variance measures how far spread the data is from the mean. And if something has 0 variance, it means the data doesn't at all spread away from the mean, and that means the data is all equal to the mean. Okay? All right. Okay, so the next example we're going to look at is this one where you have a random variable x that's uniform 0 to 10. So you know a lot about that. You know for a uniform AB random variable, the mean is b minus a over 2. So you have that the mean is 10 minus 0 over 2, which is 5. And the variance is b minus a whole squared over 12. So 10 minus 0 whole squared over 12, that's 100 over 12 or 25 over 3. Okay? And that's right here what I said in terms of a and b. So what does Chebyshev tell you? The probability of x minus 5 being bigger than 4. So that is less than or equal to the variance, which is 25 over 3 divided by this k squared. That's divided by 16, which is 0.52. Okay, so that's 25 over 48. That turns out to be 0.52. But what is this exact value? So if you have an interval from 0 to 10, the probability that you're at least 4 away from the mean. So here's the mean. The probability that you're at least 4 away. So that's the probability whether you're in 0 to 1 or 9 to 10. Well, that you know is the length of those intervals added, 2 over 10. That's 0.2. But Chebyshev told you this probability is less than or equal to 0.52. So Chebyshev doesn't give you very nice bounds, okay? It's just giving you some kind of bound, and sometimes that's all you need, that it's away from 1 or something like that. That's all you need, that, you know, this is good enough. But if you're looking for something accurate, Chebyshev won't do that for you, okay? All right. So next, let's look at this pretty known result. It's called the weak law of large numbers. You might have heard more the strong law of large numbers, and this is the weak law. So what do we have here? If you have a sequence of independent, identically distributed random variables, okay? So all of them, xi is independent of xj if I is not equal to j. And they're identically distributed. So all of these xi's, they have the same distribution. They're all uniform, or they're all exponential of a certain parameter. All of them are normal with a certain mu and a certain sigma, or all of them are binomial with the same n and the same p, you know, whatever it be. They're all the same exact distribution, but they're independent, okay? and they all have finite means mu. Then what does a weak law of large numbers say? If you take the average of n of them, x1 plus x2 blah 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 plus xn divided by n, then that minus the mean, okay, so you have x1 plus x2 over n minus the mean, the probability that that is bigger than or equal to epsilon goes to 0 as n goes to infinity. So what is this statement telling you? It says that with probability 1, x1 plus x2 plus dot 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 xn over n, so the average of these xn's goes to mu with probability 1. That's what this is saying. The weak law says that with probability 1, x1 plus x2 blah 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 goes to the mean. Okay, and the strong law, what does that say? That says a little bit more. We're not going to cover it, but just so that you know you've heard it over here. The strong law says it doesn't, this average x1 plus dot 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 plus xn over n doesn't just go to mu in probability, but if you pick every omega, what's an omega? Omega will be a sequence. What will that sequence be? It will be, I'll just write it down. If you have x1 of, you perform all these infinite experiments, x1, x2, blah, blah, blah. So perform it, and that will give you one of the omegas, one of the results, okay? And then if you look at this whole set of these infinite sequences, and if you pick any one of these omegas, for all of them, you have that the probability of this average x1 dot 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 plus xn over n that goes to mu. Okay, so this tells you that this average of the xi's goes to mu in probability. The strong law says it goes to mu for every omega. Okay? All right, anyway, so we have the weak law, and this says that this goes to mu in probability. All right, let me just write that over here. The probability that this mean approaches mu as n goes to infinity is 1. All right. And also, I mean, what is the expectation of this guy? You know the expectation of that guy is also mu. What is the variance of that guy? Just so out of being able to calculate it, what is the variance? Well, what will it be? It'll be 1 over n squared, and then you're adding up all the variances of xi's. Well, what are each one of the variances of xi's? Let's say it's sigma squared, so it's sigma squared over n squared. All right? And then what does Chebyshev say? Chebyshev says that the probability of x1 plus dot 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 plus xn over n minus mu is bigger than or equal to epsilon is less than or equal to the variance of n divided by epsilon squared. Okay, now fix your epsilon and take a limit as n goes to infinity. What's going to happen? This goes to 0 as n goes to infinity. So for each fixed epsilon, this quantity, it goes to 0 as n goes to infinity. So you know that this probability is, and that's exactly what we have. The probability that that goes to mu is 1. Okay, so that was just a quick proof of that using Chebyshev. Okay. Okay, fix epsilon and apply Chebyshev. And for each epsilon, this goes to 0. So you know that you can, if you want to also take epsilon equal to 1 over m, then you know that this bigger than or equal to 1 over m goes to 0, n goes to infinity. So you know that the probability of this average out here going to mu is 1. Okay? All right. So anyway, that was a weak law of large numbers. Now, one of the biggest results over here that we look at, actually the last biggest result we're going to look at in this class, is the central limit theorem. Okay, what does the central limit theorem say? Well, intuitively what it says is if you add up a whole bunch of independent random variables, then that new random variable that you created by adding up a bunch of them, it's approximately normal. Okay? And these xi's don't even have to be identical. They can be different. They don't have to be identical. They do need to be independent. They can have different means, different variances. That's okay, but they do need to be independent. Okay? But let's first look at let's just look at the central limit theorem in the case where they're identical. So all the xi's have the same mean mu, and all of them have the same variance sigma squared. All right? So central limit theorem says that if you look at this random variable, the sum of these, this approaches a normal random variable with mean n times mu, and of course you want the mean to have this mean of this underlying stuff, and of course you want the variance of what you're getting closer and closer to have the variance of exactly this. So this approaches a random variable that's normal, mean, n mu, and variance n sigma squared. Okay, so what does that say? If you look at this sum and subtract the mean and divide by the variance, standard deviation, the square root of the variance, then that's approximately normal 0, 1, right? So since this approach is normal as n gets bigger, so for large n, you can say this is approximately normal, but the central limit theorem actually says in the limit, this equals normal. So if n is large, this quantity, let me write that over here. If n is large, this is approximately normal 0, 1. And in the limit, it actually equals normal 0, 1. Okay? All right. And what do you mean by in the limit? You're talking about this random variable looks like a normal random variable. So the probability that this random variable is less than or equal to a is approximately phi of a. Okay? So you can say, let me just say that over here before you're taking a limit. For large n, the probability of x1 plus x2 plus xn minus n mu over n square root sigma, oops, sorry, I meant the other way, sigma square root n less than or equal to a. For large n, this is approximately phi of a. And as n gets bigger and bigger, this actually goes to phi of a in the limit. Okay, so that is the central limit theorem. Central limit theorem says if you want to find out how the sum of many random variables behaves, well, when you add it all up, it's going to approximately look normal. Okay? And this is exactly how we do normal approximation of binomial. If binomial n is large, then each one of them, x1, for binomial random variable, you have x. Suppose you have binomial, this is binomial np. What can you let x be? X can be x1 plus x2 plus xn, where xi is the result of the ith trial. And that is 1 if the trial is a success. And it is 0 if it is a failure. And if you add up all these xi's, you get x, and that's binomial np. Okay, so really this whole normal approximation to binomial does come from the central limit theorem. Okay. All right. So let's look at a couple of examples of this. In the book, there are several nice examples covering this, 3A to 3E. I've listed the page numbers over here. We're going to look at a couple of them. All right. Okay, so that's this is the back of the book, the homework problems that I've done. I've done 8.1 and 8.2. Okay, so now let's take a look at an example using the central limit theorem. I'm going to look at example 3A. I want you guys to look at the rest of the examples in the book. Ask me if you have any questions on those. Okay, so let xi be the ith. Oh, sorry, I have to read you the question. Okay. An astronomer is interested in measuring the distance in light years from his observatory to a distant star. Although the astronomer has a measuring technique, he knows that because of changing atmospheric conditions and normal error, each time a measurement is made, it will not yield the exact result or exact distance, but merely an estimate. As a result, the astronomer plans to make a series of measurements and then use the average value of these measurements as his estimated value of the actual distance. If the astronomer believes that the values of the measurements are independent and identically distributed random variables having a common mean d, which is the actual distance, and a common variance of 4, how many measurements need he make to be reasonably sure that his estimated distance is accurate to within 0.5 light year? Okay, so this question to me as a mathematician is not well formed, because what does reasonably sure mean? Well, what we'll do is we'll get a formula in terms of n, and we can even see in that as n gets bigger and bigger, that the probability of x being closer to d gets larger. Okay, so what do we have? We are taking multiple measurements. So we'll have these random variables will make up. Let xi be the ith measurement. Okay, the xi's are all identically distributed and they're independent. Their expectation is d, which is the true distance, and their variance is 4. All right, he's going to look at the average of these xi's, and the question is how large should n be so that the probability that the estimated distance is accurate within 0.5. Well, what does that mean? That the actual distance d and the estimated distance, the distance or the absolute value of their difference is less than or equal to 0.5. Okay, so we want to find out what this probability is. Okay, so let's replace x by summation xi over n. And we have this new expression in the probability. Okay, and now let's just rewrite this absolute value inequality without absolute values, and we want that the summation xi minus d, summation xi over n minus d is bigger than or equal to negative 0.5 and less than or equal to 0.5. Okay, we want to apply the central limit theorem to this. What does the central limit theorem say? The central limit theorem uses this quantity, summation xi minus dn over square root sigma times n, where sigma is the standard deviation of each of the xi's. Okay, and central limit theorem says that this is, I should write really equal to phi of n as n goes to infinity. Okay, this limit, or really I should say the limit of n going to infinity of this probability, that equals phi of a. Okay, all right, so, well, what do we have? We have, in our expression, we have this quantity, but we want to get this quantity to be able to use the central limit theorem. Okay, so let's take a look at our expression, which is 1 over n summation xi minus d. Take a common denominator, and we have summation xi minus dn over n. Okay, now the numerator looks like what we needed in the central limit, in the central limit theorem over here, right? The numerator looks like what we wanted, but the denominator we have an n instead of a sigma times square root n, and we can fix that by factoring out square root n and multiplying and dividing by a sigma. Okay, so if you multiply and divide by a sigma and factor out a square root n, then now over here, this is exactly what we have in the central limit theorem. Okay, what am I doing? I'm looking at the inequality we're trying to estimate, and to try and use the central limit theorem, we need to make the quantity look like the quantity in the central limit theorem. Okay, so now let's come back to this quantity whose probability we were looking for. And I showed you this little side calculation. The center, we've replaced it by this, which this calculation shows you is the same. Okay. And now this part over here is all we need in the central limit theorem. So let's get rid of this sigma over square root n by multiplying throughout by square root n over sigma. That's a positive quantity. You don't have to do anything with the inequalities, okay? By the way, this is less than or equal to. Okay, now this is exactly what we have in the central limit theorem, right? And central limit theorem says that that's approximately z, or it gets closer and closer to z as n goes to infinity. Okay, well, if that's z, then you know that if you were looking for the probability of z being between negative alpha and alpha, what is that? That's this area. And if you work it out with this little picture, you can see that what it turns out to be is 2 times the probability of z less than or equal to alpha minus 1, okay? Because 2 times the probability of z less than or equal to alpha will be this whole red region and this shaded black region added together. And what have you done? Now, you have counted this area once, this region once, and this region twice. But if you count, so you want to remove one of these, remove one of these, remove one of this to be counting just one of these center regions that we have. And that means removing 1. So it's 2 times p of z less than or equal to alpha minus 1. That'll be exactly this probability. Okay, so really I should put in approximately here. So this is approximately 2 times phi of square root n over sigma times 0.5 minus 1. Okay, so what is this pictorially? In the picture, this is the region. Okay, what is this in the picture? It is the region between square root n sigma times 0.5 and minus square root n over sigma times 0.5. This is this region, this whole thing. And what do you know? As n goes to infinity, what happens to this right and left boundaries of the shaded region? As n goes to infinity, these go further and further apart, and that probability does go closer and closer to 1. Okay, so you know that this, in fact, will get closer to 1 as n gets to infinity. Okay, And depending on how close you want it to 1, you can pick a larger and larger n. But the key was to notice that as n gets larger, this does get closer and closer to 1. So if you want it to be 95% sure, then you want to have that this probability is bigger than or equal to 0.95. And then you could find out what square root n needs to be or what n needs to be. Okay? You can figure that out. Let me just write that down just so that you know. And oh, by the way, sorry, I should replace these n's with 2. I mean the sigmas with 2. Because sigma squared is 4. So we know that sigma needs to be 2. I'll just leave it sigma there so you know where that 2 came from. Okay. And suppose you wanted the probability to be bigger than or equal to 0.95. So what will you do? You would want 2 times phi square root n over 2, 0.5 minus 1 to be bigger than or equal to 0.95. Okay, so 2 times phi of square root n over 2, 0.5 to be bigger than or equal to 1.95. All right, divide that by 2. And you want phi of this to be bigger than or equal to whatever this is, 0.975. Okay, so then you would pick from the tables. So what should this be? Square root n over 2. So you pick the smallest n as your lower limit, or smallest integer n as your lower limit that satisfies, well, so what is this? This is phi of, now you have to look in the tables to see that 0.975 is phi of what? I'll just tell you in a second. So 0.975 is 1.96. Okay, so this is phi of 1.96. So you want to pick the smallest integer n as your lower limit of what's the minimum number of readings you need to take, where this is 1.96. So square root n is equal to 2 times 1.96 over 0.5, or or 4 times 1.96, and n equals, or the minimum n is 4 times 1.96 square. And you know, you would need n to be an integer. So whatever this turns out to be, you pick the smallest integer that's at least as big as this. Okay, pick the smallest integer okay, I mean just telling you. Okay, so let's suppose it was 2. So 4 times 2, that's 8. 8 squared is 64. You know, this is a little bit less than 64, so maybe n should be, maybe this was 63.5. Okay, then you take n to be 64. Okay, that's just an example. I haven't worked out what this number is. Okay, so I hope that this makes sense to you. It's a nice thing to use when you're adding up a bunch of random variables and you want to estimate what their sum will look like, or what their average will look like. And you know that when you're adding up a bunch of random variables, no matter what the distribution is, the average looks like a normal random variable. Okay, so that was example 3A. I want you to look at example 3B in the book. Look also at example 3C in the book, example 3D and 3E, and let me know if you have any questions. Okay, and make sure you understand them. And just one little comment. If you had random variables that were not identically distributed, okay, then what does the central limit theorem say? Let's go back up to the central limit theorem. Then what you do is over here, you don't subtract n times mu, you will subtract mu1, which is the expectation of x1. And then also subtract mu2, subtract mu3 all the way till mu n. And in the denominator, you'll have the square root of the sum of the variances. Okay, so that's central limit theorem for independent random variables that are not necessarily identical. That is theorem 3.2 in the book. You can take a look. And that's where we'll end chapter 8. And you can take a look at the homework problems for that, and let me know if you guys have any questions. I'll be happy to answer any of the problems. I have put answers to questions 1 and 2 over here, and let me know if you want me to give you solutions to any of the rest. Okay guys, I hope that made sense, and take care. Bye.